Section 6.6 is the last section in Chapter 6, and we're going to finish out looking at how to solve some logarithmic equations and some exponential equations. And we've already seen a few of these kind of problems, but knowing what we know from Section 6.5, now that kind of opens up a whole new set of problems that we couldn't answer before. And so that's what we're going to look at in Section 6.6. It starts out saying, you know, we've seen how you can use the definition of a logarithm to solve an equation. So that's, you know, what this right here is, showing that we can rewrite a logarithm as an exponent, and then from there just kind of work it through and solve it for an equation. One thing we did say we have to keep in mind is sometimes we have to check our answers once we get this solution and make sure that they also work in the logarithm, keeping in mind what the domain of the logarithm is. And so you would need to go back and plug in that value to make sure that that 1 minus 2x is a positive value. So that's something we'll keep in mind as we go through and solve these equations. So just jumping in here, it says solve each logarithmic equation, express irrational solutions in exact form and as a decimal rounded to 3 decimal places. So when we get to the end of the question, we'll hit, you know, both of those and make sure we cover what that means exactly. But example 1, 2 times log base 5 of x equals log base 5 of 9. Now this looks kind of not fun. We got those logarithms in there. But one thing we said, there's a property, if you'll recall, if log base a of m equals log base a of n, the bases of the logarithm match, then we can drop the logarithm notation, right? That's almost what we've got here. Both sides are base 5 logarithms, but we've got this 2 that's really kind of making things rough, not really helping us out. But what we can do is move that 2 and make it an exponent on the x. Now notice both sides are single logarithms, base 5, and so we drop the logarithm notation. We get x squared equals 9, and from that we know that x could be positive or negative 3, right? Both of those can be squared to get a 9. Now, both are solutions to x squared equals 9, but are both of them solutions to our original equation? And if you look at this, that plus or minus 3, if you say, you know, 2 log base 5 of negative 3 and 2 log base 5 of positive 3, this one's good, this one's not. We can't have negative values inside that logarithm. So really the only solution we have to our equation is x equals positive 3. So you got to check those, make sure they work in the original solution or original equation that you're given. These values inside the logarithm have to be positive. Okay, next one. Again, this looks a little tricky, but we got base 5 logarithms on the left. So we could say, all right, if we could somehow make these both single logarithms with a base of 5, we'd be set. So let's go ahead and combine this left side together. We know that since we're adding, we can multiply those together. Now that right side, we can kind of go 2 directions here. We can rewrite the right side as a base 5 logarithm. If you'll recall, that's log base 5 of 5 is equal to 1, right? So that's one route. So we could say log base 5 of this is equal to log base 5 of 5, and then drop the log base 5 notation, just like we did in that last question. Okay, an alternate route, we could have gone from here and rewritten this as 5 to the 1 equals this right here, rewrite it as an exponent, right? Notice we get the same thing. So just know that's kind of an alternate method, and you'll see that fairly often where there's more than one way to get to the end with the correct answer. But however you get there is fine as long as it's correct. So let's FOIL this out. Whoops, let me get my other color. So x squared, that's going to be plus 8x plus 12 equals 5, and then subtract 5 from both sides. Set it equal to 0. We can now factor that. And then our two zeros here are -7 and -1. So we get two solutions in the end, but again, are they both solutions? You go back to the very beginning. We've got -7 and -1. Do they both work? If you put a -7 here, -7 plus 6 is -1. That's a problem. Okay, so -7 is out. Can't use it. If you put a -1 in here, -1 plus 6 is 5. -1 plus 2 is 1. That's good. Both are positive. So the positive one works. I'm sorry, the -1 works. So that's our solution. So you just go back and test them. Make sure that these values right here have to be positive when you plug in your x values. Alright, let's see if we can combine both sides together, get a single logarithm on both sides. On the left side, see if you agree that we can put those together with multiplication. So this is natural log of x squared minus 4x. Over here, we just have x plus 6. Can't really do anything fancy there. Now we can drop the natural logarithm notation since we have single natural logarithms on both sides. This is a quadratic. It's got the x squared. So let's subtract an x from both sides and a 6. We get x squared minus 5x minus 6. From there we can factor it. X minus 6 times x plus 1. And our two zeros, positive 6 and -1. Now again, do they both work? Do any of them cause negative values inside these logarithms? 6 is good here. 6 minus 4 is 2. That's good. 6 plus 6 is 12. That's good. So 6 is okay. Let's try the -1. Well, right off the bat, natural log -1 is no good. So we toss it. Doesn't matter what happens in the rest of them. If it fails in one of them, then that's enough to say it's not a solution. Okay. On to the next. Those are all logarithmic equations. Now we're going to look at some exponential equations. We had a method for solving exponential equations that we used where we would set both sides up as powers of the same base. Just notice what we've got here, both powers of 4, and then just set the exponents equal to each other using this property right here. Now we can't always do that. We saw an example of that a couple sections ago where we couldn't rewrite one side as a power of the other of the same base. So when we do that, we can use logarithms to help us out and get solutions. So let's jump in. 2 to the x equals 5. Can't really work that out. But what we can do, we can go a couple different routes. We can rewrite it as a logarithm. It becomes a log base 2 of 5 equals x. And then can't we say that this is natural log 5 over natural log 2, right? Change the base formula. And then from there, notice the instructions say we want irrational solutions in exact form and as a decimal. And so what that means is we've got our exact form right here. This is our exact. That means written with logarithms. For the decimal, we're actually going to work this out. What's natural log 5 over natural log 2? We get 2.322. I think we had worked that out in the last section. But that's our decimal value, rounded to 3 decimal places. Exact form, decimal form. Make sure you pay attention on the instructions of the homework. You know which, so you know which form to write your answer in. 8 times 3 to the x equals 5. That's almost the same as one we just had, but it's got this 8 times kind of tagged on the front there. But we can take care of that pretty easily. Just divide by 8. 3 to the x equals 5/8, or we could call that, I think it's 0.625. Yeah. And then from there, kind of proceed the same way. That's log base 3 of 0.625, or natural log of 0.625 over natural log of 3. So there's our exact form. And then for the decimal, we just work that out. What's natural log 0.625? Oops, divided by, make sure you close your parentheses, natural log 3, negative 0.428. So there's our decimal value. Okay. So that's kind of one way you can do these is if you have a single x as an exponent, get that power on by itself on one side, and then rewrite it as a logarithm and use the change of base formula. That's what we did for both of those. Now here, this is a little bit trickier. 5 to the x minus 2 equals 3 to the 3x plus 2. Two different bases, both have a variable x in them. Here we'll have to proceed a little bit differently. But the way we're going to do that is, kind of the tricky thing about solving this equation is the x is up in the exponent. X minus 2 and 3x plus 2 in the exponent. But we can actually remedy that. If we take a logarithm on both sides, it doesn't matter what base you use. I'm going to use natural logarithms, but you want to use something you can put in the calculator to get those exact solutions. So use either a natural logarithm or a base 10 common logarithm. Do that on both sides. Now you can pull down these powers. Whoops, and I forgot my natural log 5. So we get something like this. Now you got to keep in mind that natural log 5 and natural log 3 are just numbers. They don't look like regular numbers, but they are. Okay. And so why do I say that? Well, we still need to solve this for x. Okay. So to do that, we need to get x by itself on one side. So let's distribute the natural logs through here. So we get x natural log 5 minus 2 natural log 5. We get a 3x natural log 3 plus 2 natural log 3. Okay. Now let's get our x terms on one side. That's this guy and this guy. So we're going to subtract 3x natural log 3 from both sides. Okay, and let's go ahead and add 2 natural log 5 to both sides. Okay, this is a little weird, but just go with it. Okay, these are going to cancel. On the left side, we're going to have x natural log 5 minus 3x natural log 3. On the right side, we've got 2 natural log 3 plus 2 natural log 5. Okay, so we've got the x's on one side, constant terms on the other. Now we somehow need to separate this x from all this other mess. So let's just factor it out. Just like that. Factor out the x. Now we can just divide. Again, all these natural logarithms are just numbers. It just looks messy because it's not written as kind of what we would normally write it a number as. So we just divide that out, and we get that x is this whole mess right here, 2 natural log 3 plus 2 natural log 5 over natural log 5 minus 3 natural log 3. So that's the exact form. Not the easiest problem. Okay, it's a lot of just manipulation. There's not a ton of tricky algebra there. It just gets messy because of all the natural logarithms. All right, now from here we still need the decimal form. What I would suggest is don't bite off more than you can chew here. So what I mean by that is don't try to punch this whole thing in the calculator at once. Maybe start with 2 natural log 3 plus 2 natural log 5. Just take the numerator. Make sure you get all the parentheses in where you need them and all that, and that'll take you and figure out the numerator. Then divide, and if you'll open up a set of parentheses, you can punch this whole denominator in. Natural log 5 minus 2 or 3 natural log 3. It's going to look like this. So we get negative 3.212. And that's the decimal. Okay. Again, not the easiest, but hopefully you followed through some of that there. 4 to the x minus 2 to the x minus 12. Now this one is another one that's a little odd. Here we've got 2 powers of x and then a constant. And so if you encounter one like this, you actually want to go about it almost a totally different way. We're actually going to start by saying that 4 to the x is the same as 2 squared to the x. And you can actually switch these around and make that 2 to the x squared. It's the same as 2 squared to the x. And so what we have really here is a quadratic. If you say that y is 2 to the x, do a little substitution here. This is the same as y squared minus y minus 12, right? If you just replace the 2 to the x's with some temporary placeholder variable like a y. And you can factor that. It's y minus 4 times y plus 3. And then from that we get, you could say y minus 4. Well, actually we could say, just jump straight to it, the zeros here are 4 and negative 3, right? Remember, we're not actually solving for y, we're solving for x. And y is 2 to the x. So this is saying that 2 to the x equals 4 and 2 to the x equals negative 3, right? Now if we try to solve those, 2 to some power is negative 3 actually doesn't work. There's no solution to that guy. Over here, 2 to what power is 4? That would be 2 to the second, right? So here we get that x is 2. It's really a weird kind of equation, doing that substitution halfway through, and then factoring and then unsubstituting, replacing the y back with 2 to the x. We get x is 2. But hopefully that makes sense. And I guess that's it. Disregard this homework. So that's it for Chapter 6. If you have any questions, by all means, please let me know.